Hello, I'm Quinn Brodsky, and today I'll be presenting about an analysis of the photoelectric effect performed in JLab this semester. So the photoelectric effect is the phenomenon of when light, which is incident upon the surface of a metal, is energetic enough to kick the electrons off of the surface. And then we refer to the electrons as photoelectrons. And each metal has a characteristic property that we call the work function, which here is denoted by phi. And this basically determines the energy needed to free the electron from the surface of the metal. And basically, if we use the conservation of energy, we can calculate that the maximum kinetic energy of a photoelectron is given by k equals h nu minus phi, where nu is the frequency of the light. And this was discovered by Heinrich Hertz in 1887, and Einstein in 1905 took Hertz's results and then combined it with Planck's idea of quantization to formulate the idea that light comes in photons, which is quantized in packets of energy as h nu, where h is Planck's constant. And although we did not perform the experimental setup and procedures, I'll just quickly outline them below, but I'm mostly going to focus on the analysis. So first, a function generator is hooked up to a green LED, which creates a periodic function where we can adjust the period, the amplitude, and like the general shape of the function. And here we use square pulses to just open and close the gate with a period of 5 microseconds sent to the LED. And the LED produces green photons with a wavelength of 560 nanometers. Then the photons are sent through a cloth, which acts as an attenuator and just reduces the number of the incoming photons. And the photons which remain hit the photocathode, which causes the electrons to be ejected from the photoelectric effect. Then the electrons are sent into the photomultiplier tube towards its first dynode. And the photomultiplier tube is an apparatus that takes in the signal from one electron and amplifies it using its dynodes, which are sheets of metal which have a work function much lower than the sheet of metal that the electrons originally came from. So this allows many, many more electrons to be ejected via the photoelectric effect. It's also, the PMT is also hooked up to a high voltage supply that basically controls its gain. Then we transfer this signal to the oscilloscope where we can visualize the signal for analysis. And we note that both the function generator and the PMT are connected to the oscilloscope. But we didn't actually do any of that. This procedure was used to generate a couple sets of data that were given to us. And we are going to refer to two of the data sets A and B. And these data sets contain the oscilloscope voltage from the photomultiplier tube as a function of time. And the interval of time was fixed to 2,500 nanoseconds for all the sweeps contained in both data sets A and B. And each of the data sets contains 100 sweeps of 2,500 nanoseconds. So first, we took this data and read it into an analysis code. We inverted it so that the voltage goes as it's increasing because electrons have a negative charge. They would make the voltage go negative, but we just flipped it so it'd be easier to look at. The baseline, which is the signal present on the scope when there is no actual signal being read, which is a background signal, is indicated on the plot with the blue line here, and I've pointed to it with an arrow. And finally, we fit the data to a Landau probability distribution using the pi Landau function. And here the fit is indicated by the orange, the thick orange line. And I've also indicated the best fit parameters for the Landau on the plot. And we've also associated this with an uncertainty which is given by the jitter, which is basically the absolute fluctuation of the equipment. And here we just see it as some random noise over there. To further investigate, we calculated the number of photons seen per pulse by using the SciPy function called find peaks. We used a threshold peak height of 5 times the jitter and also a threshold peak width of 9 nanoseconds. And this was basically in order to not include the data that just comes from purely noise. And here I've indicated the peaks by these red dots on top of the data. And for simple sweeps, like in data set A, it's pretty easy to identify these peaks. You can go through the data manually and verify that it gets it pretty much most of the time. But for data set B, these sweeps are a little bit more complicated. And so the peak finding method is a little bit more faulty and we miss a couple of peaks here and there. But we see that if we have a sweep which is purely noise, we can tell that this is just a background sweep. We don't identify any peaks, which is what we were intending to do. So due to some of the failure of the find peaks function, I've associated an uncertainty in the counts of the number of peaks of 1 in 10 for data set A and about 2 in 10 for data set B. I want to note that from here on out, I'm going to assume that one pulse was created by one photon. This isn't actually true, but I'll discuss this later when I talk about error analysis. So once we found the number of peaks, which I have said corresponds to the number of photons for each sweep, I histogrammed the information to find the distribution of the photon counts across the data. And then I fit these to both a Gaussian and a Poissonian distribution. And this was basically done so I could acquire the average number of photons per sweep, which is given by the mean of the fits here. And for the Gaussian fit of data set A, I have a mean of about 0.97 photons per sweep. And for the Poissonian, we have about 0.58. And then for data set B, I have a mean of about 8.6 given from the Gaussian, and from the Poissonian, I have a mean of about 8.9. And so I compared these means to a mean that I calculated by just summing over all the photon counts over all of the data, of the sweeps in the data set, and dividing by the total number of sweeps in this data set, which corresponds to 2,500 nanoseconds. And for data set A, that number results to be 0.65 photons per sweep and about 8.2 from data set B. And you can tell by comparing these means to the means that you get from the Gaussian and the Poissonian distributions that they're fairly close to each other. They're not exactly within one standard deviation of each other, but you can see that for data set A, neither of the fits are particularly good. And for data set B, the means are pretty close. You can also kind of test how good the fit was by looking at the chi-squared value. We see that the Poissonian distribution for data set A has a huge chi-squared value, so that's probably not a great distribution. But both of the chi-squared values for data set B are pretty low, which indicates that the Gaussian is a fair approximation for these data sets. Also, it's important to note that for data sets with larger means, the Gaussian and Poissonian fits are both fair approximations, and as the mean increases, a Poissonian distribution becomes more Gaussian. And you can think about like evening out the other tail with more counts to kind of flatten out the distribution a little bit more. So as I mentioned before, the find peaks function was not always successful. So I associated an error of about 1 in 10 for data set A, 2 in 10 for data set B. And so I've defined sigma NA and sigma BA for both of those uncertainties. And so this comes into play when I calculate the mean values. So I had to propagate the error when calculating the uncertainty in the mean. But the mean is linearly related to the error in the peak finding, so the mean error is the same as the counting error. We also note that the statistical uncertainty for the system is just the standard deviation over the square root of all of the counts. And so for Gaussians, we see that this is about 0.57 for data set A. Sorry, the variance is about 0.57, so the standard deviation is about 0.75 for data set A. And for data set B, the variance is about 1.5, so the standard deviation is about 0.15. So these comprise the statistical errors for this experiment, and they're unitless since we've counted them in numbers of photons. Finally, I calculated and plotted the cumulative average, which is a cumulative sum over the data sets, also called a cumulative distribution function, which I've indicated by CDF. I fit this plot to a linear model where the slopes are M and they're shown on the plots there. The fact that the CDFs are linear means that there are no big jumps in the photon counts, which is consistent with the distribution shown earlier. And we can also calculate another version of the mean for the photon counts by multiplying the slope by the time sweep interval, because the slope is in units of photons per sweep, and one sweep is 2,500 nanoseconds. So we can get a mean for data set A, which is about 0.7, a mean for data set B, which is about 8.2, which is pretty much the same as what we got with the other calculated means. So now I'm going to discuss some of the error we had in the experiment. As I said before, the first source of error was the calculation in the number of peaks with the peak finding method. And like from comparing it with manual observations at the peaks, I associated the uncertainties that I denoted here, sigma NA and sigma NB. With this uncertainty, we associate that error, and we have to propagate that with when we calculate the mean The propagated error in the average counts mu bar A and mu bar B, which is the ones where I just add all the photons together and then divide by the total sweeps, are given by the equations in this table over here. I've also added the statistical uncertainty, which is given by the standard deviation over the square root of all the data, the number of sweeps, which I've also indicated in this table. And I wanted to address the assumption that a single pulse can be caused by only one photon. That's not actually true. So I evaluated the probability that we would find a photon that has been created by find a pulse that has been created by more than one photon. And in this experiment, we used a threshold of 9 nanoseconds as a threshold width to discriminate between pulses. Using data set B, there's an average of about 8 photons per sweep, where one sweep is 2,500 nanoseconds. So our rate is about 8 events per 2,500 nanoseconds, which means 3.2 times 10 to the 6 events per second. And so we can use the probability distribution here, the Poissonian probability distribution, to try to calculate the probability that 2 photons occur within 9 nanoseconds. And we plug this into the equation and we get a very small probability of about 0.04%. So our assumption that we assume that one pulse was caused by one photon is a pretty good assumption, but I'm still going to include this uncertainty called sigma Poisson. And this is going to be an extra term included in the sigma mu bar. So by comparing the optimal mean, where the optimal mean is the mean acquired from the Gaussian Poissonian fits, and the manually calculated mean, which was acquired by adding up all the photons, dividing by the sweeps, we can conclude that the linear averages mu bar I are a pretty good approximation for the optimized averages mu I. And the CDF indicates that within one data set, the distribution of photons is pretty regular. And the Gaussian and Poissonian fits also imply that the number of photons per oscilloscope sweep of the PNT follows the parent distribution of a Gaussian or Poissonian distribution. And this is useful because Gaussians and Poissonians are simple and effective methods of modeling data. And it's especially powerful in this example, given that the physics behind the photoelectric effect has really profound conclusions. And particularly if we consider the Poissonian distribution, that implies that the experiment models one of a counting experiment where you just count the number of occurrences of a thing, which indicates that light behaves as countable discrete objects, which are what we call photons. I also wanted to mention potential ways of improving the experiment. And the primary way I think this could be improved is just by a lot more statistics, because I think you could see that from data set A, the low statistics made the Poissonians and the Gaussians not great fits. And also more varied data, because I think comparing data set A to data set B was just much more complex. We got much more interesting results with that. And I also would be interested to test the validity of the Gaussian limit of the Poissonian as the mean increases. And other than that, I would try improving the peak finding method and try it on other data sets to see how effective it is. Thank you for listening. A special thanks to John, who is my wonderful lab partner, and to Maya Reese, with whom I've had many conversations about this experiment. And also thanks to Professors Pallas and Robinson and to Songbek for their helpful hints and mentorship. Are there any questions?